for a couple of minutes, then we can start. Nobody else joins. By the way, how was your exam?
It was okay, sir.
Okay, you are from electrical or EC?
Easy, sir, easy.
Okay, that makes more sense. So anyway, let's begin. So welcome everyone. This is NOC 26W86 NPTEL tutorial session on semiconductor devices for next gen FETs. More than mood, a physics perspective. So the course instructor is Professor Sudeb Dasgupta from IIT Roorkee. I am Debashish from IIT Kanpur. So as you know, we go live every week Saturday from 3 to 5. So this we are at week 5, right? So let's begin. So the first question it is asked that the MOSFET can act as an amplifier in what region? So what do we mean by amplifier?
Sir, it means that we amplify the input signal given to it, right?
Okay, so let's say I draw a MOSFET. Let's take an NMOS. So this is gate, source. Let's say body is shorted to source, and this is your drain. So what are the first things? First, you need to bias this, right? Then you will be biasing this, let's say at some VDD, or let's add some resistance, and this is, let's say, VD. Let's say this is VG. Okay. So how will I get the amplification? Whatever voltage I give here will get at this node, or how does this work? So let's say this is my output node, right? So basically, if I draw the input and output characteristics, so let's say this is my VD versus ID. ID is this current flowing through the transistor. ID, this is VG. So as you know that this plot looks something like this, and your at the output it will be something like this, right? So what do I mean by amplification? Where should I apply my input signal to? At
Sir,
which
to the gate,
terminal?
sir. Gate.
Okay, let's say I am applying an input signal to the gate. So let's say this is V in, and let's say by some resistance I'll take the output at this V out at the drain end, right? So what do we amplify basically? Do we amplify the DC voltage?
No, sir, we are amplifying the AC voltage.
We amplify some AC voltage, and what is the term for that? Let's say this is the point VG, that is this point. Okay. So what happens if we apply? Okay, I got wrong color. Wait a second. So this is this and this entire stuff. Let's say this is orange. Okay. So let's say I have a small signal on top of that, right?
Yes,
So
sir.
this signal is my V in, right? So what I'll get an output. I'll get an output swing of this much. Okay, let's say this current is passed to a 1 ohm resistance. Okay, so this is what we mean by amplification. Okay, is that fine?
Yes, sir.
So first thing is that you can directly can see that my this, by the way, this curve is called transfer characteristics, because this is transfer from input to output. This curve is called output characteristics. Okay. By the way, how do I check my amplification in case of output characteristics? How do I see? If I change my gate voltages, what kind of curve we get? We get something like this, right? So this is basically VG1, VG2, VG3. Okay. So this difference is basically the output, and the difference between these two signal is the input. Okay. So we'll explain that mathematically, that why it is so. But the one thing we observe is that my output current versus input voltage has a slope of, means as the slope increases, it is better for amplification, right? So basically, if I could have a this type of line, then around this point, I can even amplify a very small signal to a very large value. Do you get that?
Yes, sir.
So, but what about the output? Output current versus output voltage. How should the slope be for amplification? For the time, that for amplifiers, you generally bias at this region, right? Or the saturation region. This you know. But why so? If this is my VDSAT line, so this will be my saturation region, this side, the yellow highlighted portion. You know that your amplifier should be biased at this region. Can you Tell me why that so? Why is that so? So for that, let's construct a two-port network. So this is basically your MOSFET only. So this is one, this is two, and this is your common terminal, right? In the MOSFET parlance, this is gate, this is drain, and this is source. Fine. So this is, let's say, V1, this current is I1, this current is I2, this voltage is V2. So a two-port network we can analyze using any of the Z, Y, A, B, C, D or H parameters. So as discussed in last class, let us try to construct with Y parameters. Okay. So let's say your I as a function of V1 and V2. Okay. Do you agree with that? I will be a function of V1 and V2, and similarly
Yes, sir.
I2 will be a function of a different function of V1 and V2. Okay. Now what you are doing, you are applying some small signals. So let's say you are V1, you are making some V1 plus delta V1 small voltage, and V2 you are making at this plus some small excursion you are giving. So do you believe that that will create an excursion in the eyes as well? So basically what I meant to say, your I1 will also have a small component due to this, and which will be a function of V1 plus this small delta V1, comma V2 plus this small delta V2. Is that okay so far?
Yes, sir.
Now, uh, so let's say this V1 and V2 are your DC values, okay? Which also we will call this bias. And this V1 and V2 are we will call AC or small signal. Why small signal? We'll just see now. Fine. So can you do the Taylor series expansion of this? So can I write this as V1 comma V2 plus df1 times df1 derivative with respect to V1, and then it will be V1 plus delta V1 minus V1. Similarly, you will have partial derivative with respect to the other independent variable V2, and then it will be V1, V2 plus delta V2 minus V2, then plus you will have D2F1 dV1 times something plus D2F1 dV22 times something plus D2F1 dV1 dV2 times this, the cross product, and also higher order terms, provided that these all derivatives are calculated at V1. the DC points. Okay, so just
Yes, sir.
for clarity, just let me put 0 here so it will be clearer for you. So 0, so let's say 0, this is 0, 0, 0 means now your DC components. So 0, 0, then we'll have here 0, 0, and so forth. Where's that? Wait a second. Okay, and this bias points are calculated at V01. So this 01 and 020 I just introduced to make sure that you are uh, getting it right, and then I can just safely change this to equal sign. Fine. So now note that this term and this term are same.
Yes, sir.
So this I can cancel. And what about these terms? Higher order terms of Taylor series, can I ignore? If I assume that, so this cancels, this cancels. So if delta V1 and delta V2 are small, that is your small signal, higher order terms can be ignored. For example, if I have zero point 0.1, then what is the square of that? 0.01, right? It gets smaller every time. If you go to getting it cubed, then if you take power raised to 4, right? So you can ignore those terms and keep only the linear components, these two. Higher order terms, oh, what is happening? Am I audible now?
Yes, sir.
Oh, sorry, I lost my network. Okay. So, yeah. So what I was talking about that, these higher order terms can be ignored, right? So then what you are left with is delta I1 is equal to dF1 dV1 computed at your DC point times delta V1 plus dF1 dV2 computed at DC point times delta V2. Fine. Now note this very carefully. This is your small signal current. These are your small signal voltages. Fine. So this I is basically nothing but your F. So your dF by dV will be di by dV. And what does that correspond to? Some type of conductance, right? So this term is basically your Y11 parameter, and this term is basically your Y. Can you tell me what is this? Y12,
Sir, I want to.
right? So this delta I1 is equal to Y11 times delta V1 plus Y12 times delta V2. Similarly, you can compute this as delta V1 plus Y22 times delta V2. So what have we seen that this my Y parameters, this Y parameters are small signal parameters.
Yes, sir.
Similarly, your Z, A, B, C, D, H, all parameters are small signal parameters. Fine. This is the point I wanted to make clear first. Then what we'll do, we'll take a simple MOSFET amplifier and see what are the ideal condition for voltage amplification. Okay. So let's say this is my voltage source Vs. Let's say this is my Rs, the source resistance. This is the MOSFET and I am getting my voltage at this point. Okay. So this becomes the MOSFET which we denote with our Y parameters. So by the way, are you okay with this notation? This is a small signal notation, right? You can note that I have not used any bias. Small signal equivalent. Okay. What you are familiar with in small signal equivalent is this. This is what you are more familiar with, right? Correct me if I am wrong.
Yes, sir.
But we will not use this. This is what I have drawn is much more simpler version. In my small signal sense, my DC biases will be grounded, right? AC grounded, that we call AC ground.
Hmm.
So this is more convenient for us to use. This when we will discuss amplifiers, if we do discuss, that becomes helpful, right? But you need to just make sure that what are the nodes and all. So basically this how I draw it conveniently. I keep my MOSFET symbol, I ground my source, I add my, let's say this is my R0, I add my R0 here between drain and source, and this is my V. So this, if this is my V, what I note that this current is my GMV. As simple as that. Then how much current is coming in and how much current is coming out of this node, this makes the analysis much more simpler. Okay. Unless you will use your KCL, KVL in these loops, this gets somewhat untidy for me. So we'll not, these are the same things, understand please, but we'll keep using these symbols. So if you can see that I am keeping only the small signal input, the source resistance, the MOSFET, which I will replace it with Y parameters, and then my V out and load resistance, right? So if that is so, so let us point out the currents. So this is my I1, this is my I2, this voltage is my V2, and this voltage is my V1 as per our small signal, as per our small signal notations. Okay. So if that much we have done, so can I write my current equations? I1 equals to, already we know, Y11 V1 plus Y12 V2. I2 is equal to Y21 V1 plus Y22 V2. This much we know. What are the other equations? What are the unknowns here? I1, I2 are unknown. V1, V2 we can find out, right? From what relation we can find out V1, V2? Let's say if I just look into the input side, so my Vs minus V1 divided by Rs gives me I1. Is that clear?
Yes, sir.
So I will write it as G of S Vs minus V1 or I1 plus V1 times Gs equal to Gs times Vs. Fine. So this becomes my, let's say, equation 1. This becomes equation 2. This becomes equation 3. Similarly, at the output side, I have this, right? V out minus V out by RL gives me I2. For a two-port network, always remember that the current direction is coming into the terminal. That is also our passive sign convention, if you know what that means. So my I2 is nothing but minus GL times V out. So what we'll do, from these four equations, can I get an expression of V out divided by Vs, because that is my amplifier gain?
Yes, sir.
Can I get that?
Yes,
Will
sir.
it be okay if I write the final expression and you can calculate and verify it yourself?
Hmm.
Okay, just let me see if I have it somewhere. Okay, so your V out is basically, so what is V out? V out is basically your V2. That also you can see, right? So I can simply write here V2. These are the same nodes. So amplifier gain is equal to V2 by Vs will be of the form Y21 times Gs divided by Y11 plus Gs times GL plus Y22 minus Y12 times Y21. So these I am leaving from 1 to 4. Show this. Okay. So this will be the form of your gain, amplifier gain, in terms of your small signal parameter of the MOSFET in common source configuration. For the time being, we are considering that only. So we need to make some assumptions. So what are the assumptions? Assumptions are that my Y11 equal to 0 and Y12 equal to 0. Can you just check and let me know if that makes sense? So what is your Y12? This is your Y12, right? Y12 is what? When V1 is equal to 0, so Y12 is I1 by V2 when V1 is equal to 0. That means what? In my MOSFET, I am connecting gate to 0 because my V1 is 0. Gate to source voltage should be 0. And I am applying some voltage at this node. This is V2. And they are trying to find us what is the current flowing through the gate, right? So do you think that the gate current can be sufficiently small to ignore this component? First of all, of course, there is an insulator. Although capacitor lets you pass AC signal, but as the voltage is not at exactly one plate of the capacitor, but it is somehow connected. Let's see, there will be some resistance in this line. So what are your capacitor plates? Your capacitor plates are this and this. So your signal is not directly applied to the capacitor plate, right? So the AC current, that is your I equals to C dV dt, will be very small. So that is why this component can be ignored to 0. Okay. So this is justified approximation. Fine. Similarly, your Y11 component you can also ignore, although it is more difficult to ignore this, provided this gives you your gate capacitance that we have discussed in our last session. So although for the time being we'll ignore this. Okay. So if I ignore this component and this component, so what am I left with? My A will be V2 by Vs is equal to minus Y21 times Gs divided by Gs times GL plus Y22, right? So this Gs gets cancelled. So this becomes Y21 divided by GL plus Y22. Okay. So now can you tell me, if I, for a good amplifier, A should be large. So what should be my Y21 ideally? Ideally should be from this expression for large A, for large gain, what should be my Y21? Larger or smaller?
It
Tell me
should be,
this much.
it should be larger. Y21
So,
must be larger.
so what is the largest component ideally is infinity, right?
Yes.
And what should be my Y22?
Should be small as possible. 0.
So ideally should be close to
0.
0, right? So
Mm.
if I draw now V1 versus I1, sorry, I2, and I plot V2 versus I2, so this plot, so this gives me some kind of this nature, right? Because the slope is y1 y21 tends to infinity. And what about this? This gives me this kind of behavior, or the slope y22 tends to 0. Now what is my drain and source terminal? What are the terminals? So this is nothing but my id, this is nothing but my vg, this is nothing but my vd, and this is nothing but my id. So that is why if I draw my characteristics on top of this, the MOSFET characteristics, what are the regions we should bias my amplifier to? I should bias my amplifier to a region where I have the higher slope in case of in the transfer characteristics. And for that, what do I need? For that, my VG should be greater than VTH, threshold voltage, right? Let's say somewhere here is your threshold voltage. So I have to bias, or my, because the bias point will also determine, right? My bias point also determines the y11 small signal parameters, because it is a nonlinear characteristics. The derivative will depend on at what point I am differentiating the curve. So my bias point should be in the inversion region, or we call it above threshold. And what about in case of output characteristics? My bias point should be in the region where my output characteristics is almost flat. What is that region? That is my saturation region. So is that clear? So why I bias? So basically my VD should be greater than VD sat, right? Somewhere here will be your this VD sat value. So these two should satisfy when I am using the MOSFET as an amplifier. Is that clear?
Yes, sir.
So by the way, what is the real component of Y21? So Y21 is basically, so the real component of Y21 is basically nothing but your I2 by dV1, that means dID by dVg. So what is this component we call? This is my GM, right? Transconductance. And what about Y22? Y22 is my GDS, or 1 over RDS, right? Or you call it sometimes R out as well. Fine. So this
Yes, sir.
expression, what is the expression? Minus GM times 1 by RL plus 1 by RDS. Can you recon this expression? Have you seen this expression
Yes,
somewhere?
sir.
What is
Yes,
this?
sir.
This is the gain of a common source amplifier, right?
Yes, sir.
This is exactly the same
Without
expression
without a
that
source
we,
resistance, correct?
sorry?
Sir, without a source resistance, right?
Yeah, without source resistance, of course. My source is grounded,
Hmm.
right? So this
Yes,
is the
sir.
structure we had started with, right? Source is grounded. I had only, this was my RL.
Yes, sir.
Fine. So this is, our analysis also shows that for a good amplifier, I should have my RDS as high as possible. Similarly, my GM also as high as possible. So that leads to this region of operation, and in this case, this region of operation. That is where my amplifier should be biased to, right? That is why I am bias my amplifiers in the saturation region. Okay, we should be very clear that where do we bias our amplifier and why do we bias at that region. Fine. And also please be thorough with this. If you are planning to do higher studies, This is one single tool that you have to be very thorough with. Okay, Taylor series expansion. You will keep encountering your infinite series every time, believe me. Whether you are doing harmonic distortion analysis, whether you are doing periodic steady state and anything for that matter. Fine. So let's move on. So calculate the built-in potential barrier in a PN junction. Consider a silicon PN junction at T equals to 300K. That means room temperature, doping concentration, this and this. So built-in potential means my this are shorted or in
So
equilibrium.
there will be an internal electric field, right, between the P and junction.
Sorry.
So there will be an internal electric field created in the PN junction.
Yeah, right. So let's say this is
So the
my
amount of
P
voltage
side.
we need to overcome it, right?
Sorry.
So the amount of voltage which we need to apply in order to overcome this electric field, that's the built-in potential.
No, no, that is not. So I have not applied any electric field. So
Okay.
I have to, I am in thermal equilibrium. Fine.
Yes, sir.
So this is my Pn. What is my Na? P side doping is 2 into 10 raised to 17 per cc. And N side doping is 10 raised to 15 per cc. So my depletion region will be somewhat like this. Do you agree?
Yes, sir.
So what, by the way, built-in potential a concept calculated at thermal equilibrium. So what is thermal equilibrium? We had discussed it in the first class. What does thermal equilibrium means? Can you quickly summarize the points?
So no flow of current.
No, last time also you said that, right? What is the first point? Only source of energy is constant temperature, right? Only source of energy is constant temperature. No net carrier flow at any cross section. No net energy flow through any cross section. And what was the last point I mentioned that most of the books fail to cover is that principle of detailed balance. That means this cross section can be as minuscule as possible. Okay. So if you apply some voltage, no, then you are applying other source of energy, which is not valid in case of your thermal equilibrium. So when you want to calculate your thermal built-in potential, there should not be any potential difference between the P and N side. Fine? Is it okay?
Yes, sir.
So now how do you calculate your built-in electric field, built-in potential? So First, let us quickly draw the band diagram. So let us draw the vertical lines. So equilibrium, what is the first condition we should meet?
Equal Fermi level.
Constant Fermi level,
Hmm.
right? Then P side highly doped. So my EV will be very close.
Yes, sir.
This is my EC. Then N side moderately doped. So let's say this will be my, so let's say this will be my EC, and somehow here will be EV, EC, EV, EC, EV, EF, right? So it can extend in the quasi-neutral region. Then the band bending will be like this. This line. Okay, this is how your band diagram will look like. So how will your potential look like? How will your potential look like? So what is potential? So d psi by dx is equal to minus electric field, right? And electric, and also we know that energy is negative potential, q times potential, right? So if your energy bands are like this, so your potential will simply be like this. This is your psi, okay?
So it will be,
Also,
so it will
yeah,
just be the inverse of the
it will
this.
just be the inverse of the energy line,
Okay.
right? Scale, if you can, if you want to calculate it numerically, you just have to divide it by q,
Okay, sir.
right? Let's say this is some reference potential, and let's say this is some psi, we call it, let's say psi 0. So what is your built-in potential? Built-in potential is this much between this and this. This is your VBI or psi BI. This difference is your built-in potential. And why is there a potential? Because of the depletion charges, right? You can see
Yes, sir.
that N side is having positive ions, P side is having negative ions. So where will the potential be higher, at the positive or at the negative? Of course at the positive. That is also what we are seeing, that the positive side is, this side is more high potential with respect to the negative ion side, right? Because you understand that beyond these points, beyond this and beyond this, there is nothing. This is quasi neutral, right? It is equivalent to, you do not have, you see, you do not have any band bending. So no band bending in this region. Whatever the band bending is happening is between this region only, inside the depletion region only. Why so? Because what is band bending means? Band bending means non-zero slope in energy lines E. So if your d psi by dx is equal to minus E, so can I write E is equal to 1 by Q dE of dx from this equation and this equation? So this I am using as electric field. This Roman E is for energy. Okay. So band bending will happen when there will be some electric field. There is no electric field, that is why. Because why will electric field be there? This is neutral, right? This is neutral. So there will not be an electric field. So their bands will not bend. The slope of the energy bands will be zero. All the band bending will be confined to the depletion region only. Fine. So now if I have to calculate electric field, I can easily calculate from this relation. If I have to at all plot, so electric field will be what? Let's say this is the axis of this. This is I am plotting electric field with respect to, let's say, some x, and this is 0. This line is 0. So what is the electric field? Negative slope of this line. So till this point negative slope is 0, right? So electric field will be exactly 0. Then the slope of this line is increasing and then decreasing and then again becoming 0. So negative of that will give me something like this profile of electric field, right? And at the junction I will have my Emax, or maximum electric field. From that also I can calculate rho as well. So what is rho? D electric field by dx is my rho by epsilon. What is this? This is my Gauss law. So my rho profile will be rho of x will just be the opposite, just be the derivative of this. What is the derivative of this line? Negative slope. So till this I'll have 0. Beyond this I'll have 0, and then my linear will become constant. So I'll have some negative, and then at this point again my slope is becoming 0. A sharp jump, then again some kind of linear profile. So I'll have this. So do you see the same thing? While what you are accustomed to is studying this first, then plotting this, then plotting this, and then plotting this. What I have shown you, you can start at any place. If you have all the concepts in place, you can start from energy band diagram, draw potential profile, electric field profile, and then the charge profile. Or otherwise you can assume full depletion and start with this as well. Start with this, then integrate, plot this, integrate, plot this, and just revert, you get the energy profile. Is that okay?
Yes, sir.
Now we want to calculate the built-in voltage. Fine. So built-in voltage is the gap between this two potential. So can I write built-in voltage is exactly the gap between these two lines divided by Q? Can I write that built-in voltage?
Yes, sir.
So if I just copy this and let us just remove the unnecessary things. Okay. So this line, so this is the junction, metallurgical junction, and these blue lines are the depletion edges. Fine. This is my EC. So I want to calculate the band bending. So let us draw EI as well. Okay. So this is my PN junction. So at what point I have the intrinsic part of the device? So this is my intrinsic part of the device, this particular point. Because why it is intrinsic? Because at this point my EF and EI are coinciding. Is that clear?
Yes, sir.
So you see one important point to note, if doping of the P side is not equal to doping of the N type, the point at which the junction is intrinsic is not at the MJ. This line is called MJ or metallurgical junction. So you see that the point of intrinsic it inside the N region in this case. Fine. So now I want to calculate the band bending. So can you tell me if the band bending in case of, let's say this is ECP and this is ACN. So do you agree with this? ECP minus ECN will give me the built-in potential. Fine. Similarly, do you agree these are the same? EI of P minus EI of N, EV of P minus EV of N. Are these the same thing? Can I take any of the lines? Can I take any of the lines? I can, right? Because this is band gap, which is a material property. This does not have to do anything with the type of doping, right? So Eg will be constant throughout X, even in the depletion region, because the material, base material is silicon. This we have discussed in the first class. So what I'll do, I'll take this one. because this is much more easier to discuss. And I will calculate these two distances separately, this gap and this gap. That is what I will calculate, EI of P minus EF plus EF minus EI of N. Okay, and this will give me Q times VBI, or the built-in potential. Now can you tell me how can I calculate this? I have N equal to NC, or if I write it this directly, can you confirm if you are agreeing with this? Let me know. EF minus EI by KT. Is that okay with you, this relation?
Yes, sir.
This is okay, right? So P is
Yes.
again Ni, because Ni is equal to Pi, intrinsic concentration, exponential EI minus EF. Let's say this is N, this is P, divided by KT. So what will be EF? What will be EF N EF minus EI for N type is equal to, if I just take, this will be KT ln N divided by Ni. So I can write this as KT ln Nd divided by Ni. Okay, assuming these two are the same, 100% ionization and whatnot. Okay, at room temperature, mostly 100% of the Nd dopant ions will be ionized. Similarly, for this, I can write EI minus EF KT ln P by Ni, that is KT ln Na by Ni. Fine. So what will be the
Yes.
sum of these two? Sum of these two will be
EIP minus EAN.
EIP minus EIN will give me KT ln Nd by Ni plus KT ln Na by Ni. So this is KT ln NaNd divided by Ni square, that is equal to Q times VBI. So your VBI boils down to KT by Q ln NaNd by Ni square. So if you calculate this, you have Na, Nd. What is your Ni for silicon? 1.5 into 10 raised to 10 per centimeter cube at 300 K. Fine. So this becomes your at 300 K, KT by Q is 0.026 ln 2 into 10 raised to 17 times 10 raised to 15 divide by 1.15 whole square times 10 raised to 20. Calculate this, you will get your built-in potential. Okay. So can you tell me what is the current at this location? At any location? Okay, just tell me one thing. At any location, if I take this region, this depletion region, will there be any carrier movement?
Yes,
Will
carrier
the,
movement will be there.
right? But then what about the equilibrium condition? Does it
So,
get
but net
violated?
carrier, no, it does not, because the net carrier moment will still be zero,
Right. So there also will be current flows due to the carrier movement,
but it will get
but
cancelled.
cancelled, the drift and diffusion component will get cancelled by each other, right?
Yes, sir.
Do this mathematically and check. So whenever you define this no equilibrium condition, this has to be very precise, that no net carrier flow. Similarly, only source of energy can be constant temperature. This is the term thermal, and principle of retail balance is the manifestation of that. Okay, so this is how you calculate your what do you call it, built-in potential. Fine. Another interesting fact about the built-in potential, VBI cannot be measured. Do you know why? Do you know why VBI cannot be measured?
No,
So what do you need to measure something? Some kind of
voltage.
voltmeter, right?
Yes, sir.
So as soon as you connect some probe, no, at these two locations, what will that create? It will create a
Potential difference.
metal semiconductor Schottky contacts or ohmic contacts. So that and once these two are connected with some voltmeter, so this entire system forms a loop, and you by KVL every voltage will get cancelled. So you will not get anything in your voltmeter, this output. Okay.
Mm.
So that is why built-in potential is something which you cannot measure. So there are multiple times you will be asked this tricky question that how do you measure your built-in potential? You should clearly state that it cannot be measured, because as soon as I connect the measuring equipment, it creates a potential difference with the system which cancels out the built-in potential. Fine?
Yes, sir.
Okay. So, yeah, what is the primary characteristics of a Schottky contact? What is a Schottky contact?
So metal semiconductor contact.
Hmm, okay, so let's say this is metal, this is semiconductor. So, see, issue is that there are multiple misconceptions around this subject. Okay, so let's say semiconductor is of N type and also of P type. Fine, and
Yes,
let's
sir.
say this is your metal. So what is metal characterized? What are metal characterized by? Their work function, right? Let's say work function of metal is phi m. work function of semiconductor is phi s. So let's say phi m is greater than phi s, and in another case phi m is less than phi s. Okay, so there can be four cases. Fine. So if your phi m is greater than phi s in case of n-type semiconductor, this gives you Schottky kind of contact, which we will discuss what is Schottky kind of contact. Fine. And similarly, if phi m is less than phi s, you will get Schottky kind of contact. In other cases, you will get ohmic kind of contact. We'll explain what is Schottky, what is ohmic. Okay. So one thing we'll do, what I'll explain for these two n-type. Okay. What I expect from you. Similarly, you can plot and draw the band diagrams and do it for p-type semiconductor for your own satisfaction. Okay. From now on, don't take anything for granted or for given that it is, if somebody has said so, so it should be like that. Always verify this. Okay. More so in this today's age of misinformation and so on. Fine. So let us start with this. So by the way, what is ohmic? What is Ohm's law?
Voltage is proportional to current at all temperatures, did not provided temperature is constant.
This is ohmic. Okay. This is Schottky. Ohmic contacts let the current flow from both side of the, means the from reversible current flow is allowed. That means what? If I just change the polarity of the battery, current will flow in the other direction. That is what this part means. Fine. But in terms of Schottky contacts, only in one side current will flow in one direction, and in other direction current will not flow. Fine. So by
Yes,
definition,
sir.
this kind of contacts are used for rectifying behavior,
Yes, sir.
right?
Yes, sir.
Now we'll see how metal semiconductor contacts form Schottky barriers. Okay. So first let us take n-type and phi m greater than phi s. Fine. If that is so, let us consider it is in equilibrium. So first case we will consider equilibrium, then we will consider forward bias, then we will consider reverse bias. So equilibrium means my, what is constant at equilibrium?
Fermi level.
Fermi level is constant. Fine. Let's say this is the metal semiconductor junction. Left side is metal, this side is n-type semiconductor. Fine. So Fermi level of this phi m. So this is my E0, and let's say this is my E0. So this is phi s, Q phi s, this is Q phi m, and phi m is greater than phi 0, right? Similarly, if this is n type, So I'll have EC close to Fermi level
So,
and then EV.
so just one doubt, sir. Sir, why is 5m greater than 5s always?
No, no, not always. It is. I will also show you this case also, right?
Oh, okay. For this case, if 5m is we are
Yeah, yeah.
considering 5m is greater.
This is the case. One case.
Okay, okay.
Fine. So then what we have studied from the first lecture is that for the continuity of local vacuum electric field, bands will bend
Yes, sir.
and these bands will follow because Eg and electron affinity are constant for the material, right? So
Yes.
now
Yes, sir.
what is my, this is my EC, is that clear? Because for metal, EF is itself EC and EV. We have shown, right? For metal, conduction band is very close to this. EC and EV coincides and sometimes it gets overlapped. So EC, EV, EF, everything is at the same line. We have done this, right?
Yes, sir.
So if I just want to plot EC, EC will be like this. Why I am concerned about EC? Because it is an N-type material. So more number of electrons and electrons transport or gets free or move around in the conduction band, right? Whenever we will talk about valence band, you need to take care of, whenever you will do at home for P-type materials, you need to take consider the valence band. Okay, got it? So if that is so, so let's say now you have electrons present here, right? In this conduction bands. So what does electron see? Electron see a barrier, energy barrier. This energy barrier is called Schottky barrier. Okay. So electrons cannot travel from one place to another. So for the electron to travel from N side to P side, I need to lower the barrier. Let's say in forward bias, how do we do that? So in forward bias means, so the diode symbol is like this for Schottky diode. Okay. Now in this case, I am applying positive here and negative here because this is N type. This is my forward bias. Fine. So what will happen to the Fermi level? What will happen in the Fermi level?
So there will be actually a change, right?
So there will be a
Change in
change.
Fermi level.
Let's say this is my now EFM and let's say this is my EFS. And this gap between them is what? Is the applied bias.
So we are applying positive potential to the metal side, right?
Right. Let's
Okay.
say this is V. So this bias will be V. So positive
Hmm.
side, if I applying positive potential, so my Fermi level will go down, right?
Yes, sir. Sir, I just want to ask one more thing, sir.
Yeah.
Sir, that means that if we apply positive bias on a p-type, that means the Fermi level of metal will be greater than the semiconductor, right? It will
No.
be the other way around, right?
Fermi level. See what we are drawing in the energy band diagram. So energy band diagrams, implicit assumptions are electronic energy, right?
Yes, sir.
What I have shown you, electronic energy is related to potential with respect to Q times potential. So if
Yes, sir.
potential increases, energy band lowers because of this negative sign.
Okay.
So now if you have a Fermi level, let's say like this is material 1, this is material 2. Now let's say material 1 you are applying at a higher potential with respect to material 2. So either this will go down or this will go up. It does not matter which one you take. That because potential as a single quantity is nothing, it has to be referred to some reference potential, right?
Yes, sir.
Fundamental law. So that means why I can do this and mention this is the applied bias, or I can just make this at this place and up it and mention that this is QV. These are the same thing.
Okay. So it will hold good even for this P type.
It does not matter. I have seen this is material, right?
Yes, sir.
Any type of material, P type, N type, different kind of material. Fermi level, if potential is upping, see potential I'm upping from with respect to what? Equilibrium, right? Equilibrium there is a potential. Whatever the
Mm.
material is, if I increasing the potential of this material, Fermi level will go down.
Okay. So it's
Irrespective
always
of
with
P type,
respect to
N
electron
type.
energy, right?
Yes, yes.
Okay.
So in this case, if I am applying positive potential at the metal, so metal Fermi level will go down. Now everything will remain same. So this will be, let's say, metal work function will be something like this. Then your semiconductor, this is up, right? So this will be your E0, EC will be here, and EV will be somewhat here. So now again, the local vacuum level has to be continuous. So it will be something like this, and EC will be again following the E0 because these are the same material. So now what is my E0, or where the holes will get conducted or the electron will conduct, is this, right? Where is the electric field now? I have applied plus to minus, right? Electric field is this direction.
Yes, sir.
Where will the electron flow? The opposite direction. So these electrons, now does they see any barrier? It does not, right?
No.
It sees a valley, it sees a fall. So it
Mm.
will pass and current will flow.
Yes, sir.
This gives to the positive half of your Schottky or the on state of your Schottky barrier. Now what about the reverse bias case? In the reverse bias case, you are applying negative potential to this, positive potential to this. Let's say this is V. Okay? I'm just reversing the polarity. So what will happen? This will be now
So
my
this
Fermi
time
levels.
metal will be higher.
So this will be my EFS. This will be my EFM. Now this is my E0. Somewhere here will be my E0. The here will be my EC, and here will be my EV. E0 again will follow the slope. Then EC will also follow the slope, right? Then EV will also follow the slope. So let me be very clear at this point. This finishes here, okay? And then there is a jump. Fine. So now what is the, so the electrons at this place will see more larger barrier,
Yes, sir.
right? So electrons will not be able to cross. So that creates a off state. or no current. That creates this case. So this is what is you call as rectifying contact. Okay.
Okay, sir.
And also one question is that why there is no bend in the energy band in case of metal? Why I am showing the band bending in case of semiconductor only?
Hmm.
So I have already answered this. What does a band bending means? Electric
Bandwidth
field is
is,
present.
yes, sir.
If electric field is present inside the metal, that means what? Charges are present.
Hmm.
Can we have charges inside metal?
No, we cannot.
That is why my in case of metal band bending will be almost zero, right? So you have, if you have noticed that I have already drawn the straight line, but in case of PN junctions it is not so. Your P side also you get some band bending in the depletion region, right?
Yes, sir.
So we note these minute details carefully. And now let us discuss the ohmic case. So ohmic case, N type, but your phi m is less than phi s. Okay. So what will happen? So let's say equilibrium, forward bias, reverse bias. Equilibrium EF is constant. Let's say this is metal, this is N-type semiconductor. So this is, let's say, E0. So this is your E0. So this is your EC. This is your EV. So by default, it is like this at equilibrium, right? And what about your N-type conduction band? Conduction band is something like this. So you can see that by default your electrons can come to metal, right? So no barrier it is seeing, or the barrier it is seeing is very minuscule at the order of thermal energy of the electrons, right? Similarly, when you apply positive bias, what will happen? You can directly tell. So I just copy this. In case of forward bias, your this portion will move up. Okay, wait a second. Okay, I'll just freshly draw. So in case of forward bias, what will happen? This will go down, this will be up. Let's say this is EFS, this is EFM. So somewhere here is your E0, somewhere here is your E0, this is your EC, this is your EV. So more band bending, this will be very much higher. So easy carrier flow, more easy carrier flow, right? Current will can easily flow. Similarly, in case of reverse bias, this will be up and this will be lower. So this is your E0, this is your E0, this is your EC. E0, EFM, this is your EV, this is your EFS, EC. So this bending will be like this, E0. This bending will be like this. This bending will be like this. So now your conduction band is like this. So in this case, although the electrons are seeing barriers, but this barrier is at the order of kT, or let's say 3 kT.
Sir, I just want to ask one thing, sir.
Yeah,
Sir, is it possible for the easier of the semiconductor side to be a bit higher than that of the metal for the reverse bias case?
for the reverse bias case, E0 of the, yeah, it is possible. E0 of the semiconductor, because E0, see what is happening. This is your Q phi M, right? And this is your Q phi S. So anyhow your Q phi S is much more than this. This is the condition. So E0 can be like this reverse bias. So in case of reverse bias also you can see. So what happens? These are, if you compare these two cases, right? This is VMS equal to 0. This is VMS, let's say, equal to minus 2 volt. So if you have minus 1 volt case, so it can so happen that these barriers are just like this,
Hmm.
right? But the
Yes.
point is that then also I am showing you the extreme case, that when there is a barrier, also the electrons can come from this location to this location.
Okay.
Okay, but in this location, in this rate case, it is of course possible for electron to come. So what do we mean? What do we mean by that? That means VMS from negative value to positive value, electrons can cross, right?
Hmm.
And what is the consequence of this? Current flowing in the both direction. That is why this combination is an ohmic kind of contact, not a Schottky contact.
Hmm.
And this kind is Schottky contact. Okay.
Okay.
So if that is so, just I will suggest you to check this too. But what is the catch in that? You need to consider the valence band. Why? Because in that case, your p type has the majority carriers of holes, and holes conduct in the valence band, right? Because in case of conduction band, holes does not have any free state to move around, or empty state to move around. Similarly, such as like electron does not have any free state in valence band, and it only can move into conduction band, holes can move into valence band only. So you need to then check the energy differences with respect to valence band, right? And for electrons, higher the electronic energy. So if I draw energy band diagram, EB diagram, let's say E1 and E2. So E1 is at a higher energy than E2 for in case of electrons. Similarly, if I consider hole and consider E3 and E4, E4 is at a higher energy than E3. Okay, the lower line has a higher energy for holes than the upper band in for case of holes. Okay, I'll suggest you just do this. If you have any difficulty, let me know. I can take this in the summary session or next session. Okay,
Yes, sir.
so if that is done, then yeah, in a CMOS ring oscillator, increasing the supply voltage will. So what is a ring oscillator? So ring oscillator nothing but odd numbers of inverters connected back to back, right? This is a this is an RO or ring oscillator. So this is 0, 1, 2, n minus 1, sorry, n minus 2, n minus 1. So n belongs to odd numbers, okay?
Yes, sir.
Minus 1. N cannot be 1. A single inverter connected back to back saturates to a value VDD by 2. Do you know that?
What, sir?
So, what is the difference between these three cases? Just tell me. This is V1, V2, V3. How will the output look like? Remember that one inverter has a circuit diagram like this. Okay. How will the output of the first inverter look like? The first case look like this one. Case 1, case 2, case 3. First start with the easiest one. What will be the case 2?
Case 2 will resemble the like no
If
case 2
this
will be
is
the exact
0,
replica of
this is
the input.
1, this is 0. So this will remain at 0, right?
Yes, sir, an exact replica of the input.
If this is 1, this is 0, this will be 1, and then 1 and 1 gets connected, so this will remain at 1. Fine.
Hmm.
What is the third one? So the output of this will look something like this, right? It will keep at 1. Let's say the green case. What about the third one? Third one is somehow by means of noise, if this inverter gets started, so if this is 0, this is 1, 0, 1. So 1 is again fed back to this, 1, then 0, then 1, then 0. Then again 0 will go back to this, 0, 1, and it goes on, right? So the output will be something like this, right? This gives you oscillations, right? And this is the case what we will discuss today. But what about the first one? So this case you read, this case also you read, and this case, believe me, will be asked in your interviews. What is the output of the
So
case
what?
one?
So won't it just be the inverse of the input?
But input and output are connected, right?
Yes, so it won't be like 0, 1, then 1, 0, be like
No.
towering way.
So what happens basically? That is where we'll come to that how this inverter, how the ring oscillator operates, right? What is the
Mm.
inverter VTC? This is V in, this is V out, right?
Yes, sir.
Inverter VTC looks something like this, right?
Mm.
This is unloaded, and this is determined by the current balance between this and this. You know that, right?
Yes, sir.
Now, what is the line where input and output are same? This is V in equal to V out, straight line. This is what this connection actually means. So what are the common solution of these two? This point, okay? This is called Vm, which will be very close to VDD by 2. So your output gets saturated at VDD by 2. Okay? This is because if you read oscillation basics, and something called Barkhausen's principle, you can easily see that for the oscillation to sustain, there has to be some delay element in the feedback path. Okay.
Mm.
So in this case, let's say this is my output, this is my input, and this is the delay element. Okay.
Yes, sir.
That is why in the third case, I am not going into the in-depth analysis of this because this question or this course does not allow me to do that. My previous course, I analyzed this thing in detail. What is delay and how we take care of that. But you just take it from me that there has to be delay in the feedback path for the oscillation to sustain. Fine. So
Yes, sir.
that is why when you have input and output directly connected, and if you ignore that the wire delay is almost zero, then you are just getting saturated at this point. Okay. So please do not make this mistake in your interviews or in the exam. Fine.
Mm.
Now, coming back to delays and inverters. So what will happen if I have, let's say, n stages, n inverters, and the delay of one inverter is, let's say, TD. The other inverter, let's say, identical TD. So what is the total delay of the inverter from input to output? Total delay of inverter n inverters. What is the total delay from input to output of this arrow? N times TD, right?
Yes, sir.
So what will be the oscillation frequency? So this is 0 to 1 is your n times TD. So what is the oscillation frequency?
1 by NTD.
1 by time period. Can you quickly check and want to correct what you have said? What is the time period of the signal?
That is just NTD.
2 times
Two,
NTD,
two
right?
times NTD. Okay.
So 0 to 1, you see, right? If this is, let's say if this is 0, this will give you 1, right? For
Yes,
0
sir.
to 1 transition, you have one NTD. Then
Hmm.
again, if it is 1, then to 0, you have another NTD. So you need to full the cycle, right?
Yes, sir.
This is what a cycle is.
Hmm.
So that is another NTD. So oscillation frequency of ring oscillator is 1 by 2 times NTD. Fine.
Yes, sir. Sir, I just
So
want to ask one more
yeah,
thing, sir.
yeah.
Sir, for this case 2 and case 3, won't there be any delay in that loop
Of course, that delay is or that delay is critical for the oscillation, right? So where
uh,
that delay is coming from? See,
from the inverter
what you are
gates?
bothered about? You are bothered about this output and this input.
Hmm.
Between this to this, you will have delay, and that
Hmm.
delay is getting translated into this
Okay.
0 to 1, right?
Hmm.
This is your entity,
Yes.
and in our case, it is 3TD. So that is determining the frequency of oscillation, right?
Hmm.
So this oscillation frequency is determined by this TD and number of stages. If number of stages are more, if N is more, frequency of oscillation will reduce.
Hmm.
Fine.
Hmm.
Now the question is, how do your supply voltage interact with this?
Hmm.
So see, this is constant. N is not a function of supply voltage for sure, because we are not minimizing anything. So what is the this of supply voltage? TD, right? TD is the function of supply voltage. We need to see how TD changes with respect to VDD. So what is TD dependent on? What is TD? Delay of one inverter. More correct term is propagation delay of one inverter, right? So what is an inverter? So let's say, just don't go to formulas and anything, just from pure common sense, can you tell me, let's say this is your load capacitance, okay? CL. CL is what? CL is nothing but the gate capacitance of the next stage. This is the gate
Hmm.
of sum, right? It is the next stage gate capacitance. For the time being, assume like that. There will be self capacitances also involved. That's when we discuss inverter in detail, we will discuss that. For the time being, assume that this is your inverter. This is V in, this is V out, and where is your VDD? This is VDD. So now you are increasing VDD. So what will happen to delay? Will it increase or decrease? So this delay is what basically, if you give some positive pulse like this, you will get some negative output like this. So this center to center, 50% of the input, let's say this is input of the inverter, this is output of the inverter. So this is, so my output is going from high to low, right? This is we call TPHL. Similarly, this delay, where the inverter output is transitioning from low to high, so my TD is defined as TPHL plus TPLH divided by 2. Okay. So this TPHL is what? TPHL is output is going from high to low. That means capacitor is fully charged. It is discharging through this NMOS. Fine? This case. And this case, when output is going from low to high, that means my VDD is getting charged at CL. So this NMOS is connected to TPLH and PMOS is this PMOS is related to TPLH and this NMOS is related to TPHL. Fine. This much is clear. Now tell me. So basically, what is happening? If I take only TPLH,
Sir,
yeah,
sir, sir, how will NMOS be TPHL? Because if this NMOS becomes low, won't that mean that the NMOS is off actually?
no. See, this is CMOS, right? So whenever, so TP, okay, just let me show you TPHL first, okay? TPHL is what? Output
Goes from high
is
to low.
going from high to low, right? So output is high means what? This is VDD,
NMOS is on.
NMOS is on.
Yes, sir.
So this is my CL and this is my NMOS,
Hmm.
right? So
Hmm.
CL is pre-charged to, let's say, VDD. So it will start
So
to
we are
discharge.
already assuming it is charged up to VDD. We are assuming it's already charged.
Yeah, of course it is already charged, right? So see, this is what, this is which node's voltage? Output, right? This node
Yes, sir.
voltage. What is this node voltage? This is high or low?
Right.
This is high, right? If this
Yes,
is,
sir.
let's say, your 5 volt. So
Okay.
if this is 5 volt, it is going to 0 volt. So
Okay.
of course it is fully charged, charged before I am going from high to low. That is the meaning of going from high to low, right?
Yes, sir.
So similarly for TPLH, so what I am doing, my this NMOS will be off and PMOS will be on, and I'll have simply CL and this is VDD. So this path will charge the
Hmm.
CL. So now this TPLH is, if you know, this is 0.69 times R on times CL, right?
Yes, sir.
Now tell me, if I increase VDD, what will happen? But just by looking at the circuit. So let's say your capacitor is what? Capacitor like a bucket, okay? This is like a, let's say this is a bucket and you want to fill it with water, right? With charge, let's say. So if my VDD increases, will it take less time or more time to charge this node voltage up to the VDD? Let's say I want to charge my CL to 1 volt, and let's say for that I need 1 picosecond. Now if I want to charge my CL to 5 volt, will I need more than 1 picosecond or less than 1 picosecond? Did you get the question? So my question is, if you want to fill the bucket with more water, do you need more time or less time
Less time
to
because it's
fill
already.
the bucket with more water?
Sir, the bucket will already have some water filled already, right?
So how does that matter? Let's say the bucket can be charged to any value, but I can fill it with any number of water, arbitrary number of water.
Hmm.
So if you want to fill 1 liter of water and if you want to fill 5 liter of water, in which case you will take more time.
5 liters. So, but the problem is that we are already assuming that there's some water already in the bucket, right, sir?
So what? Let's say 0.5 liter water is already present.
Yes, sir.
Now you want to fill it up to 1 liter. And in another case, you want to fill it up to 5 liter. In one case, you need to fill 500 ml more. In another case, you need to fill 4.5 liters more.
Okay.
So in which case you will need more time?
The second case.
Second case, of course, right? Similarly, let's say this node voltage, earlier, let's say one case VDD is 1 volt. In another case, VDD is 5 volt. So this, as this capacitor is charging, this node voltage is going up. How does capacitor charge? It charges exponentially like this, right?
Yes, sir.
So to reach 1 volt and to reach 5 volt, of course, it will take more time. So in another word, your TD will nothing but CL times VDD divided by I on. I on is the on current of the transistor. VDD is the voltage, supply voltage, and CL is the total cap. So this quantity gives you the total charge that needs to be stored in the capacitor. Fine.
Yes, sir.
And I is the current. So charge by current gives you the time or delay that is required to fill the bucket or charge the capacitor up to that voltage. So if you increase your VDD, your TD will increase. If TD increases, F oscillation will decrease. Okay. If TD increase, so VDD increases, TD increases, F oscillation of the ring oscillator decreases. Okay.
Yes, sir.
So these ring oscillators are very important circuits in case of determining, let's say you are developing some model, we want to test the robustness of the model. For that also we use ring oscillators. Another thing from process point of view, let's say you want to get some variation idea between, so let's say what is happening, this is your wafer. Okay, do you know what silicon wafer means? This comes in a
Yes, sir.
round discs. Okay, of this can be of 200 dia
Hmm.
or 300 dia. 300 is the industry de facto now, but still there are some, this is 8-inch, this is 12-inch. 12-inch dias are also available. So what happens, you slice it up, there are multiple ICs present at each places. Okay, so let's say
Yes,
this
sir.
is one IC, let's say this is another IC. Okay, now you want to fabricate this on the same process because you're one single disk, right? You cannot do this differently, another thing differently. These all are happening in the same process, but between this, let's say this is A and this is Z, between A and Z, you will have huge changes in your, let's say, doping profile, let's say length, geometry, etc. Right? And for that, for these things, your threshold voltage changes, that changes your on current, that on current changes your TD, and that changes your ring oscillator frequency, right? So how much change in the ring oscillator frequency can give us an indicator between how much change in NA or L or this kind of parameters, right? So what people does, people actually, if I zoom up,
So can we discuss in the next class because right now I have another meeting to join.
yeah, sure, you can discuss in the, we can discuss it in the next class. What I will suggest you leave and I'll just record it and post it, right? This
Okay.
particular part. Okay. So what people does is that people use multiple stages of ring oscillator inside every IC, and then they first thing one that wafer is taped out, then they first check what is the FOSC at this place, what is the FOSC at this place. So by checking the deviation from FOSC from one place to another place, they can get a fair idea about the quality of the fabrication process and if there is any corrective measures required, right? So for global process monitoring, ROs are very important. Also, ROs are placed in the location of these edges. These edges are called curve regions where these arrows will be present, which will be used to characterize the variability and process and whatnot, right? So basically, moral of the story is arrows play an important role in determining the simple circuit, odd numbers of inverters connected back to back, gives you a fair idea about multiple things from the process point of view, and also it helps in characterizing your uh, compact models, which we will discuss in the next class. Okay, so that's all for today. Thank you.